At the end, hopefully we'll have some time if there's something that you're struggling with to go through it. At least you'll feel like, oh, now I see what I can do. While you have an idea where you want to start, the difference between where you start and where you end is so great that it's hard to see how everything is going to come together. And a lot of times it has to do with the fact that we're not just working directly with sine and cosine, that we have all of the secondary trig functions in here as well. But you just have to start with something, see what happens, and if you get stuck in the middle, well, then you do an educated cheat. You go over to the other side and you start doing something with that side until you can see, hey, here's where these are going to connect up. And then you can go back to your original work and finish it up. And really, that is how these are done, because some of them just get so complex. So we've got this little multiply by a clever form of one conjugate over another conjugate to set up a difference of squares and a Pythagorean substitution. In fact, we had to do that with example 4 yesterday. You know, we used a conjugate to get things the way that we wanted them. And then it says expand only the conjugates, leaving the other side of the fraction factored, ready to divide out common factors. With one like this, it would be hard to say which side to start with, because both of them are reasonably complex, except I look at the left and I think, cotangent squared theta. Isn't there a Pythagorean identity that deals with cotangent squared that spits out something with cosecant? So I go back to sine squared theta plus cosine squared theta equals 1. I think, okay, if I'm going to get cotangent, that has to be cosine divided by sine. So that would happen right here. If I divided this whole thing by sine squared theta, I'd get 1 plus cotangent squared theta. And again, dividing by sine squared theta, that would give me cosecant squared theta over here. Okay, so I could replace, oops, and I put cosine s instead of a t. I could replace cotangent squared theta with cosecant squared theta minus 1. Now they didn't use theta. That also drives me bonkers, like we haven't seen enough of the symbols. This is phi. So we'll have to try to remember to use phi all the way through this thing. But we're going to replace this cotangent squared that we start with, phi, and see what happens. Cosecant squared phi minus 1. That's a difference of 2 squares. If I factor that, I should be able to get one of these to cancel out. Let's factor that. Might bother some of you that it's 1 plus cosecant phi. If you want to add in another step where you reverse this down here, you can do that, but we wouldn't have to. You know, it should be obvious to anybody that has any math skills that cosecant phi plus 1 is the same thing as 1 plus cosecant phi. So, bless you. Those are good kids, love. Here's why I changed colors. Is that what the right side of this thing said? Nope. You'd think, hey, if you simplify it all the way, bam, that should have been our answer right there. But not even close to what we see over here. Not even close. So now what I'm going to do is I'm going to work on the right side for a while. And I'm going to see, how do I get this to be that? And then I can go back and reverse the order and keep working with what I have in the black down here. But this is a really complex proof. So sometimes you have to do that. So I'm looking at this good stuff over here and I'm thinking, boy, I wish those were just primary trig functions. You know, there's a lot going on here. I think I'm just going to change them all into the primary trig functions. Cotangent would be cosine of phi over sine of phi. I keep wanting to write theta. I prefer theta. What's secant again? 1 over cosine of phi. How do you write tangent again in terms of sine and cosine? Sine over cosine. Okay, now seeing it like that, I see that if I just distribute that, my cosines are going to disappear. Because in the first one, the cosines will drop out, and I'll get 1 over the sine of phi. And in the second one, my cosines will drop out. In fact, what else drops out? Sines. Wait a minute. What's sine again? 1 over sine. What do you get? So secant. Look at that. Now, we can't just draw an arrow and say, here, now go this way. That was our work to help us figure out where we go with this. So now what we do is say, okay, now it makes sense. I can see how it's going to work. Would we ever have thought of this? No. We wouldn't have broken cosecant of phi up into 1 over sine of phi and then multiplied by cosine over sine. Wouldn't have happened. We wouldn't have seen that unless we worked from both sides. But now we know where to go. So now we say, all right, I use these steps backwards. So my next step would be this. And here comes the step we just would not have thought of. And that would be, I don't want it to lose the window here, but cosine of phi over sine of phi. Times 1 over cosine of phi minus sine of phi over cosine of phi. It's too big a leap. And we just wouldn't have thought, let's do all this in terms of cosine and sine and get everything together. And then that led us back to that. All right.
Do you have to put in the step where you go from 1 over sine minus 1 to that, the next step? Are we missing a step, or can you just jump like that?
Oh, I see what you mean. We can make the jump.
Okay.
I know it's kind of a big jump. Here's what Art is saying. At this point, where we go from this, directly from this down to here, there's actually 2 things that are going on. First, we'd get a common denominator over here, and then we would multiply by the cosine over sine. But because you're not going to erase that good work for us, and we're going to be able to see how you got it, we're saying it's okay to do that. That we can just put 2 steps in one right there. And what was it originally? I scrolled up there too far. Cotangent phi times secant phi minus tangent phi. Because, yeah, that other work you're just going to leave on your test or on your homework so we can see, hey, here's how you got it. And then it'll make sense looking at it backwards. But again, you don't just draw arrows and say, from here, follow me backwards this way. It needs to be a logical series of steps. So, that's your work. But this is your answer to the problem as you go through it. Now, I know at least 3 of those at the end of that first assignment, this would have been really helpful. We just didn't have time to get to it yesterday. Feeling better about that now? Like I said, it is a valid way to do the problem. Absolutely a valid way. It's a thinking way to do it. If I can't get this to work, how am I going to make it happen? So now on the next page, things get semi-easier. Yesterday, I was kind of surprised that some people, when I went to use the calculator to show you that those 2 graphs were the same, some of you maybe had never done that before. That's one of the things that I always teach my Algebra 2 students before we take the multiple choice finals is, if you want to know whether or not 2 things are the same, put them in the calculator in the graphing mode. If they graph exactly the same, they are exactly the same. So that's how we figure out whether or not they're equal to each other, those identities. If we need to, throw them in the graphing calculator. So like it says, disproving non-identities, obviously not every equation involves trigonometric expressions in an identity. How can we spot a non-identity? You know, don't waste your time if you know it's not going to work. How do you spot a non-identity before embarking on a futile attempt at a proof? Try the following exploration. Well, we're just going to kind of talk through it here. It says, prove or disprove that this is an identity. The cosine of 2x equals 2 cosine of x. In fact, this is called a double angle formula right here. It's special. It does not equal 2 cosine of x. You can't just pull that 2 out front. It doesn't work that way. So it says graph y equals cosine of 2x and y equals 2 cosine of x in the same window. And interpret the graphs to make a conclusion about whether or not the equation is an identity. One of them's blue, one of them's red. Are they equivalent? Not a chance. They're not the same graph. We shouldn't be able to tell them apart if they are the same graph. They are equal to each other. So this one says just interpret whether or not they are an identity. No, they're not an identity. So we certainly wouldn't try to prove that. You know, they're not going to work. With the help of the graph, find a value of x where they're not equal to each other. Well, right here it's 0. They're not equal to each other. X equals 0. It's not going to work because the cosine of 2x, let's see, they did that one in blue, is 1. And the cosine of, 2 cosine of x is up here at 2. So they're not the same. So we might just take one step here where we go, cosine of 2x is not equal to 2 cosine of x to make it really, really clear. Hey, 2 separate equations don't give us the same stuff. Don't give us the same y value. So 3 says, does the existence of the x value in part 2, does that prove that the equation is not an identity? That's not proof. It's called a counterexample. So it's formally not a proof, but yes, one counterexample does tell us that something is not true. So their language is a little weird here. It's not a proof, but yes, it does use a counterexample to show the false identity. And again, the G word, in geometry, you learn that to prove something, you have to prove it true for every situation. And that's what we've been doing. We are doing those proofs right now. But if you want to prove that something's false, all you need is one counterexample. You show one time when it doesn't work, and you're done. You can say, hey, this doesn't work, isn't going to happen. So this one says, how about if you graphed y equals cosine of 2x, and then y equals cosine squared x minus sine squared x in the same window? Interpret the graphs to make a conclusion about whether or not the cosine of 2x does equal cosine squared x minus sine squared x, if that is an identity. So, taking a look at these graphs, what would you say? Looks pretty good, right? Looks like one is going right over the top. So graphically, we would say yes. Do the graphs in part 4 prove that that's an identity? No, that's not a proof. You know, we're only seeing whatever part of the window they decided to graph here, whether or not it was from -4 pi to 4 pi or whatever. But that doesn't guarantee that everywhere else this is going to be the same. So no, it doesn't prove it. We would have to actually go through the steps of proving it with a formal proof. So no, we would need to prove it in a series of logical steps. That's what a proof does. It shows the logical steps coming from your initial statement, called usually a conditional, down to your conclusion. Logical mathematical steps that you can see. That'll do that. So if they ask us, to prove something and they throw in one like yesterday where it said, figure out which of these two it could be equal to first and then prove it, yeah, we're going to grab the graphing calculator. We want to take a look at it and see which of these are the same, because I don't want to do two proofs to find out that one of them doesn't work. I just want to save myself some time and use some logic. So now, look at that page, huh? Woo! Them's a lot of formulas. We're going to learn them all. Not today, but we're going to learn them all. Today what we're going to focus on is, again, just trying to prove some of these and make sure that they work. In the next group of chapters that we do after the 5125 grade, I believe it is. Yeah, when we take the test. We're going to get all of these. We will. So there's a ton of really great formulas out there. Like I said, there's some identities in calculus right here. Did you guys get the full page of them? You didn't get the full page. Yeah, there's a full page of formulas that we have that work with sine, cosine, tangent, all of our marvelous trig functions. We have to make sure they're going to work. I mean, you're not ever supposed to use anything in math unless you're absolutely certain it's going to work. So I take a look at this, and normally we would say, hey, let's start with that vicious long side over there and make it look like the short side. But in fact, for these, what we want to do is think, how could I break this up so it will look like that when I get done? And believe it or not, the first thing that catches my attention is right there, that there's a cosine x all by itself. Because what that tells me is I should investigate what happens if I break this up into reasonable pieces. So I'm going to start with my sine squared x, cosine to the fifth x. What I'm going to do is break it into things that I have a Pythagorean identity for. So sine squared x is definitely something we can use for the Pythagorean identities. But then we need this one broken up into squareds so that we'll have that one little cosine x hanging out in the back there. Believe it or not, to get what we have up there is really obvious at this point. Because I want you to look at this. You see any cosines in that? So that means anywhere we have a cosine squared down here, we have to replace that with something with sine squared. That's the only way this is going to work. So I'll leave my little sine squared x out front. Can you give me something we could replace cosine squared x with? And we will do that with both of them. What do you suppose we should do next? That one we're going to need for this. Yeah, I know, it's like a sore thumb sticking out there, but that we need. How are we going to make this mess look like that? We got to do some foil and we have to distribute it. Yeah, we do. So we're going to foil these. Now, how do I know we need to foil? Look at the powers up there. There you go. They're not 2's anymore. We need a 2, a 4, and a 6. We have to multiply all this out. So what we'll do first is multiply these two together with FOIL and just save this little sine squared x until after we're done with that. And remember, when we square something with sine, we always put the little symbol for squared right after the word sine. So sine squared times sine squared is going to give you this sine to the fourth. That's back here. Now let's distribute the sine squared of x through that first set of parentheses. So you take a small clue like, wait a minute, this is cosine of the fifth. Over there is cosine x. And you just start, you say, okay, let me separate this stuff. Let me see what I can do here. And then I notice, hey, there's no cosines in any of this, so that has to be my only cosine. How do I replace stuff that has cosine in order to get sines all over the place? Sine squared theta plus cosine squared theta equals 1. So I think you'll be able to help me a little bit more with this one. What are you thinking?
Yes. Sine squared x times sine squared x times sine x.
This looks like a power there. Oh, that's better. Boil it. Anything left for us to do? Not a doggone thing. Those are proofs. Those are proofs. Very different proofs than what we were doing over the last couple of days, but those are proofs. Yes. For an algebraic proof, we really should. If they say show that, then we're kind of off the hook, because we just want to have that series of steps. But if we're going to do a proof, it needs to be a step-by-step approach, and that equals breaks it up into those steps as we go through it. All right, so I do want to see your 4, 3, 2, 1, 0. Give me an overall between what we did yesterday and what we did today. 4, 3, 2, 1, 0. It's straight, but it's straight with algebra. Sometimes mixing those two up. Yeah, it won't be the last time we do this. It won't. It's just I wanted to see where everybody's feeling confidence level. For this. Oh, this is the one. Is it in your packet like in the wrong place? Or is it not in there at all again? Huh. Well, you'll be given this at some point here, because this is basically the list of what they're going to ask us to prove, so that we can make sure that we're using formulas that are good formulas, as we go through all these. Almost all of it. Almost all. We do expect you to memorize the Pythagorean identities and the cofunction identities in the odd even. But the rest of these, no. The rest of these, they are used rarely, which means that if you're in the real world using this stuff, you're probably looking it up. Or if you're in a job where you use it all the time, then you accidentally memorize it. But really, these would be things that you would look up. So we're going to give you those for the test anyway. But Pythagorean identities, odd, even, and cofunction, we have to know. Those. Alrighty. Let me put this back up here. And then, like I said, if you're taking a look at it now and you realize, oh, if I just did the trick where I did some stuff on the right-hand side first and then work backwards, I'd be okay. Then maybe you just want to hang on and not ask questions today. But I certainly will go over anything that anybody wants. Yeah. Sure. Grab a post-it here so I can start writing them down. I should stop the recording.